Okay guys, it's Professor Floyd here one more time, and we are working through homework set 6, and we are now on problem 4. And in this case, I've asked you to calculate the loss due to headspace in a water well sample. And so the water has been contaminated with tetrachloroethylene, which I have above my head, and the technician sampled it like you see up here. They sampled in a jar, or maybe it was just the homeowner, took a 1 liter jar and filled it halfway full, 0.5 liters, took it to the lab, and the lab technician analyzed it and found that there are 3.2 milligrams per liter in that water. So what I want to ask you are twofold. A, what is the concentration in the headspace if that 3.2 milligrams per liter is a true representation of what was in the water at the time that the jar was opened. So what was the headspace concentration just before the jar was opened? And then I want to know, if you correct for that headspace loss, what was the water concentration in the well? Because we'd assume that the well is at steady state and the air on top of the wellhead is probably in saturation with tetrachloroethylene. So we lost TCE out of the water that was sampled into the headspace of the jar. So let's get to work. So I've got a few things. I've already looked up the molecular weight, and I've already looked up the Henry's law constant. On NIST, for this one, there's probably about 25 or 30 different values that you can go with, and they're kind of ranging a good bit, all the way from 0.03-ish to 0.018. So, you know, about threefold difference. The very first one is 0.058. There's about 3 or 4 0.057s, some 0.059. So I went with 0.057. You can go with what you'd like, but I thought that was kind of the median value, since I don't really know anything else about these data that are included. So we have a jar that has half and half. The liquid was found to contain 3.2 milligrams per liter. So first, what's the concentration in the headspace? So the concentration in the headspace, so concentration aqueous is equal to the KH multiplied by the pressure. So in this case, the pressure is our headspace concentration. So our pressure equals the concentration aqueous divided by the KH. Now we're going to have to work our units out on this, obviously. So we'll get a pressure, and then we'll have to convert that pressure into particular units. And I have not specified what units I want those in. So you can express them in ppms. That's usually the easiest way to do that. So let's start off by just plugging in. We have 3.2 milligrams per liter. And then we have 0.057 moles per liter bar. So our liters cancel. We have moles and we have bar. Now I usually like to go ahead and get rid of my bar and do 760 torr per 1 bar. I keep on making that mistake tonight. It's 750 torr per 1 bar. Alright, so that's going to give me, my bars are gone, I'll be left in torr and milligrams per mole. So I still need to get rid of my milligrams. So I'm going to say 1 gram is equal to 1,000 milligrams, and then my moles, I need to get rid of those as well. And so I'm going to multiply by 1 mole per molecular weight, which is 165.8 grams. So now my grams will cancel, my milligrams cancel, and then my moles cancel, right? And so I'm just left with torr. Okay. So if we punch this in, we get 3.2 divided by 0.057 times 750 divided by 1,000 divided by 165.8. So we get 0.254 torr. And we want to know what the concentration is, so if we divide that by 760 torr, 1 atmosphere, then that gives us our concentration divided by 760, and then multiply, and then if we take that and we multiply by 1,000,000, then we get ppm. Okay, so 334 parts per million. All right. So that is our question to 1. The headspace is 334 ppm. Now I want you to tell me what was the concentration in the well, because all that mass that's in the headspace, giving the headspace some concentration, well, that mass came out of the water. So if we calculate the mass that's in the headspace and add it to the mass that's in the water, that's our true concentration in the well. So we have 334 parts per million in the headspace. We need that in some sort of mass unit, so milligrams per cubic meter is good enough for me. Multiply it by our molecular weight, 165.8 grams per mole. Divide by molar volume. We're assuming that we're at 1 atmosphere and about 25 C, so 24.45 liters per mole. And this gives me, again, remember, the units cancel out. I end up with 1,000,000 units too large, but I have a 10 to the minus 6 here. Again, ppm is not units. ppm is a placeholder, and it represents 10 to the minus 6. So the reason we can go straight from parts per million, if we multiply by molecular weight and divide by molar volume, it takes us straight into milligrams per cubic meter because of the units. So milligrams per cubic meter, and let's just calculate that times 165.8 divided by that just didn't look right. Yeah, okay, well, I guess it was. 2,265 milligrams per cubic meter. Now, of course, we don't have near to a cubic meter. So if we are 2265 milligrams per cubic meter, 1 cubic meter is 1,000 liters, and then we only have half of a liter, right? So that's going to leave us in milligrams. So 2265 divided by 1,000 and times 0.5 or divided by another 2. So that equals 1.13. 1.13 doesn't seem like a lot, but when you consider that the concentration that was found by the lab is 3.2 milligrams per liter, if we add a whole another 1.13 milligrams, then that's, well, right here we have that many per liter, so our total mass here is 3.2 milligrams per liter, and then there was only a half liter of water too, right? 0.5 liters of water. 3.2 times 0.5, so that's 1.6. So almost an equal part. left the water and went into the air. So this is why we sample for VOCs like TCE with a VOA vial and make sure we do it with 0 headspace. So anyhow, we add these up together and we see that 1.13 plus 1.6 equals 2.73 milligrams, and that was in 0.5 liters, right? Because we physically only drew a ½ liter out. So what was our true concentration beforehand? It was 5.46 milligrams per liter, not 3.2 milligrams per liter. So we lost a lot by having a little bit of headspace. What would really be a fun calculation, maybe for the exam, is to do the same thing, but to use a 40 ml VOA vial, volatile organic analysis vial. They actually hold about 42.5 mils, but we'll just assume it's a 40 ml vial, and somebody leaves a 500 microliter air bubble in it. And then how much of the TCE partitions into that 500 microliter air bubble. So maybe expect that one on the exam. I don't know.